Welcome back to ECE 320A. We have 3 more lecture sessions prior to the final exam. The final exam is in 2 weeks, and actually 2 weeks and a little less. 2 weeks minus 2 hours. You need to be here at 10:30 for the final exam on the 17th of December. A couple of items are due prior to that. Well, 3 things are due prior to that. There's a homework number 9 that's due Thursday of this week. I've made homework 10 due a week after that. That's on reading day, if that's of any benefit to you, and I've extended the time limit up to 11:59 p.m. if you're using the Dropbox. Don't expect to turn it in hard copy at that point. I think the building will be locked down in terms of my mailbox location. Hopefully that's not a problem for getting that 10th homework assignment turned in. There are teacher course evaluations. Those are online. I'm assuming you're getting all sorts of emails reminding you to complete that. Right now we have maybe a 20% participation rate. Let's try to get that up a little bit before it's due, which is the 11th of December. Today I have a long list to try to work through. I guess it fits on one screen. That's good. I tried to put them all on one line. Filter types. Let's just discuss those now that you know how to sketch Bode plots, or at least you will know by the final and definitely maybe by Thursday, since that's your homework assignment. That gives you a better feel for what transfer functions look like relative to frequency response, and you can start to build up a transfer function to accomplish a certain filtering behavior. And we'll quickly go through some of those types of filters and how we could actually realize those or build those with RLCs, resistors, inductors, and capacitors. Not that you would want to build them that way, but that gives you a way to quickly think of a physical realization or an implementation of these 4 different filter types that we'll talk about. We'll then discuss active filters with an example. Then we will talk about scaling, frequency scaling and magnitude scaling. How do you change parameter values to adjust your, let's say you have this really nice filter design, but it's designed for a bandwidth of 1 radian per second. Well, everything in this world doesn't revolve around a 1 radian per second bandwidth, and you may need to scale that frequency. You may need to adjust it. Maybe you need it to be 200 hertz. So how do you pick your parameter values to make this nice filter that is designed for 1 radian per second to actually be a 200 hertz bandwidth? That's frequency scaling. Magnitude scaling is maybe Josie only has 1 microfarad capacitors. And you go, oh, my circuit calls for a 1 farad capacitor. Josie, don't you handle those in the stock room? So the magnitude scaling allows you to convert parameters to elements that you might have more of. And you can actually put those 2 scalings together so that you can use them at the same time. You can frequency scale and magnitude scale so that you now, oh boy, I had a fire sale, maybe Black Friday you bought 110 microfarad capacitors. Didn't you see that online? Oh, that was Cyber Monday. That was yesterday. No, I'm teasing, maybe. But maybe somebody has this big box of certain parameters that they need to use. You can do this scaling to accomplish that. Then we'll go through a filter example illustrating that with a low-pass filter. And then we'll start. We haven't eaten enough maybe after the long holiday. Maybe you were fortunate and didn't eat as much as I did, but I still feel full and I'm still hungry, so go figure. But we'll talk about Butterworth. The reason that came up is Butterworth, right? Butterworth syrup. And that goes hand in hand with Butterworth filters because Butterworth filters are maximally flat, just like pancakes. So if you think of the passband frequency response being really, really flat, fat after eating all that Butterworth syrup, but flat, then we'll figure out how to design those using this Butterworth filter, and that really just says something about where those poles are located in the complex S-plane, how they're distributed, how they are located in the complex S-plane. That determines this Butterworth filter behavior. And we'll talk about how do we pick the order. Why would we want a higher order filter? Higher Q. Whatever Q is, right? But if you had a really sharp bandpass or a high Q filter, that might be important. But one way of thinking of this is how fast do you roll off in high frequencies? That depends on how many extra poles you have versus zeros, doesn't it? So if you put more poles in, you get a sharper or a faster roll off from the pass band into the stop band. So you may want to have a lot of attenuation quickly, which requires a higher order filter. And that you need to learn how to pick your filter order, and we'll try to work through an example of that. Let's get started then by filtering, which is chapters 14 and 15. And as I said, the Bode plot gives us the information that we need to start to better understand these different types of filters, and let's just walk through those rather quickly. We have the classical low pass filter, and what does its magnitude response look like? If I said, can you sketch the magnitude response in dB for a low pass filter, just ideal, I hope that you can quickly do that. You can simply say, oh, this is a low pass behavior. You could actually create a filter that realizes that or that implements that particular response with a passive device, meaning just some R's and C's. If we have a first order filter with a resistor and a capacitor, that's going to give us this low pass filter behavior, where this particular point, the break frequency or the cutoff frequency, is related to those parameter values R's and C. And there is one quick realization. It's first order because you have one energy storage device. That means how fast are you rolling off into the stop band? Minus 20 dB per decade. You might use this if you had a lot of noise in your system and you wanted to filter that out. This would be nice for removing noise. You might actually want to sample a signal, and so you want to get rid of a lot of high frequencies before you sample your waveform. You want to introduce an anti-aliasing filter. That's what you could use for this also. So this could be for rejecting high frequencies. Or that could be used for a specific case of reducing aliasing, or it's called an anti-aliasing filter. You don't want these high frequencies looking like low frequencies after sampling. And if you filter those out or reduce them, they will have less impact when you sample. That's the first type, is a low pass filter. We should be very familiar with that. The second, which is sort of its opposite, is the high pass. In terms of its frequency response in dB, it now favors high frequencies, or it rejects low frequencies. A realization, a physical realization, passive realization, again, you could build this up with resistors and inductors. And there's a first order high pass filter where this particular cutoff frequency is still related to the parameters. This is now R over L, that particular cutoff frequency. In this case, we are trying to get rid of low frequencies or reject those low frequencies. Or you might have some bias in your system, low frequency bias or a DC offset. You might want to reduce that DC bias or offset by introducing this high pass filter. Another filter type would be to selectively pass certain frequencies or a band pass frequency. In this case, we are passing intermediate frequencies. And again, all of these terms are relative. Intermediate in one setting may be different than in another setting, but we're trying to pass a certain band of frequencies. And that might be for, let's say, communication purposes. Maybe we have specific frequencies that we want to pass through our system or push out through our system. The the frequency response now might look something like that, where we are rejecting low frequencies, we're rejecting high frequencies, and we're trying to pass these intermediate frequencies. A passive realization for that, made up of resistors, inductors, and capacitors, now we string a couple energy storage devices together with this inductor and capacitor with a resistor. And now that relationship, if you derive the transfer function, which you should be able to do now or in the future, in 2 weeks, hint, hint, then you should be able to derive the transfer function, sketch the Bode plot, give the sinusoidal steady state output response, see how all of these are related. And I could just give you one problem, and that would be the whole exam. So if you miss the first step, I have to quit. I can just quit grading and just give you 10 points out of 3,000 or whatever the final is worth. Happy, aren't we, today? All right, what's the next one? We've had low pass, high pass, band reject. Here we might be wanting to reject disturbances or certain frequencies. Maybe we have some hum from the power line, 60 hertz hum, and we want to get rid of that. Reject it. A way to realize this with a passive circuit, and now you could almost anticipate what this looks like. This looks like sort of just the opposite of what we had for the band pass. Now we're measuring our output across the 2 energy storage elements, and we're putting the input in across all 3. And that now gives us a way to realize a band reject filter. Those are passive, and those help to illustrate the different types of filters that we're dealing with, but you need to also understand how to build or work with and analyze active filters. Now we put on our 2-year-old cap, right? Why? One is you probably don't want to be putting inductors in everything. Those are heavy devices, heavy little elements. So you can avoid inductors by using active filters. They don't require inductors, which are heavy little devices and expensive. That might be a reason. Cost. That usually drives a lot of different designs. You can also amplify your signal. So active filters allow more control over how you can scale the waveform. They allow more control over amplification. And a lot of times they are not as dependent on the load that you're trying to drive or that you're hanging on the end of this chain of filters. Their characteristics, meaning their frequency response behavior, their characteristics are not altered by the loads at their outputs. Let's look at an example. Now that you are becoming experts at analyzing circuits, deriving the equations that govern these circuits, this is actually a problem in the textbook, problem 1533, part C, apparently. Oh, and I even have the page number. Wow. That's on page 599. Couldn't quite make it to 600. But now what's this circuit look like? Now we have an active filter which in this class says, okay, we have this op amp. We're interested in the output of that op amp. And let's now connect that output with a resistor. Let me call that R sub 3. Here is R sub 1, R sub 2. And let me call this, or let me just go ahead and use the same capacitor values. And I'm going to go ahead and put this into the frequency domain. So this now has an impedance of 1 over SC, that parameter. And let's just use the same value of capacitor there. And now let me connect up my input between those two terminals on the input side of that circuit. And now, are you ready to analyze that, or is it clear how to analyze that circuit? Or what we might do? And one thing, first, is there negative feedback? Yes, you are feeding the output back to the inverting terminal, and that's a good thing. That now makes this op amp have well-behaved properties if you don't drive it too hard or hit the extremes. What you want to maybe keep in mind is that that's now just a big node. That capacity, you really sort of have two capacitors in parallel going in between those two resistors, and you have a feedback resistor coming back around that op amp. Meaning we really sort of have two nodes in addition to the input terminal and the output terminal. We have this particular node, which we could call node N, and let's say this particular node is called node 1. And now that I've labeled nodes, maybe it's clear what I'm trying to do. Now what I want to do is some nodal analysis, write some KCL equations at those two nodes. If I now write KCL at node 1, I'm going to have four different currents to worry about. I have this current, I have that current, and that current. They're all flowing, let's say, out of that node number 1. And if that's my node 1, I can now label that as this voltage V1. Where, let's say, the current going from right to left out of that horizontal, or through that horizontal resistor, has a current of V1 minus V sub I over R1. The current going vertically down through R sub 2 is simply V1 over R sub 2. The current horizontally from left to right through that capacitor is V1 minus the voltage at that N node. But what's that? That's 0, isn't it? Because it's tied through that virtual ground through the inverting and non-inverting terminals. So I can say V1 minus V sub N, but V sub N is 0, so I'm not even going to include it. I'm just going to say plus V1 over the impedance of that element, which is 1 over SC. That's the current going horizontally, but it's also the current going vertically up, isn't it? Because I have V sub 1 to that same node, V sub N, which we said is 0. So I can say, oh, I also have another V sub 1, and all of those currents need to sum to 0. Is it clear where that equation comes from? That's just one KCL equation, or one node voltage equation at node number 1 in terms of the different node voltages. V1, VI, VN, and VO. And I didn't have to use really VN, I didn't have to use VO for that node. Let me now combine that equation. I have two different variables. I have V1, so I have 1 over R1. I have 1 over R sub 2. I have an SC and another SC. Whoops. Those all scale V1, or are the weighting of V1, that node voltage V1, and then if I put V sub I on the other side, I have that. If I put all of these over a common denominator, and now I need to solve for V1 over V sub I to get the input-output relationship for that particular node. I then have V1 over V sub I. Now let me just multiply both sides by the reciprocal of that block left-hand coefficient, which now the R1s cancel, and I'm left with R2 over R1 plus R sub 2 plus 2R1 R2 CS, and that's now my relationship. Or I think actually in a minute I'm going to want V1 in terms of V sub I, so let me just go ahead and keep that V sub I over on the right. So here is now V sub 1 in terms of V sub I. But I probably need an input-output equation. I don't need an input to an intermediate node equation necessarily, but I could have asked for that transfer function between V sub I and V sub 1, and that blocked expression would produce that transfer function. I still have a second node that I can write a KCL equation. I can write KCL at that V sub N node. Now I can say, oh, I also have, and which way do I want to write these? Let's say that now I have all of those going in to that V sub n node, and I'm going to sum those to 0. So that now if I write KCL at little n, I have V1 over 1 over SC again, going in from horizontally from the left. The V1 current going vertically up is exactly the same. V1 divided by that impedance, and then I have this current coming in from the output. That's V0 minus V sub n over that impedance, which is R sub 3, and V sub n we agreed was 0. This is now plus V sub 0 over R sub 3 is equal to 0. Is it okay where that came from? Pardon? So now I've directed all of those blue currents into the node. So I'm summing all these algebraically the same. So they're all going in. So I can just say, oh, I'm going to call all of those positive on one side of my equation. Is that okay? I'm going to get a negative when I solve for V1 towards the output V out. Or if I now write V out in terms of V1, I now have VO is equal to, all those SCs come upstairs, and I have 2 of those, plus I get that R3 moving through, so I now have 2 R sub 3 CS times V1. If I now combine this equation with that equation to get rid of V1, I get my transfer function between V sub I and V sub O. Meaning now let me just multiply this minus 2 R3CS by that black bracketed transfer function. And that will give me my equation or my transfer function between the input terminals and the output terminals. Or I now have, for my final result, I have V sub 0, and that's this function of S, is equal to minus 2 R sub 3C, and didn't I have something else up there, R sub 2. So let me go ahead and maybe put those in the right order. R sub 2, R sub 3 CS, all over the denominator in that bracketed equation, which was R1 plus R sub 2 plus 2 R sub 1, R sub 2 CS. That's now my transfer function for this op-amp circuit. It has a couple of energy storage devices and 3 resistors. I now have the transfer function for that particular circuit. It looks maybe a little bit messy, but I can actually simplify that by assuming some particular parameter values. Suppose I go ahead and let all of these parameters be the same numerical value. R1 equal R2 equal R3 is equal to C. So I'm abusing the units, but I want the number. Let me just make them all 1. So that now upstairs I have minus 2S. Downstairs I have a couple of 1s that I will add. That will give me 2 plus 2S. So 2's are being seen throughout, and now I have V sub 0 of S over V sub I of S is now equal to minus 2S over 2 plus 2S, or that's now minus S over S plus 1. And now you should actually start to see the Bode plot, magnitude Bode plot for that op-amp based filter. that filter, the way it's interconnected, produces a transfer function having this structure. And if you forget the negative sign for a minute, what do you have? You need to look at what I have in the numerator and what I have in the denominator and start putting those together. What's in the numerator? Do you have any zeros? And where is it located? Right at the origin, isn't it? And that's one of those special cases. I have a 0 at the origin, which says that s is equal to 0, to make that vanish, to make the numerator vanish. Where's my pole? That's at 1 radian per second, isn't it? -1. So now you can sketch the Bode plot for that. If I said, what's the magnitude in dB look like for this transfer function, and now I have a 0 at the origin and a pole at -1, what would you sketch? What's the 0 at the origin produce? And now you should just sort of be virtually or physically moving your hand, right? It's going up from the basement, isn't it? It's coming up from below, and it's always sloping. It never breaks. It's coming up, and its slope is plus 20 dB per decade. Meaning at low frequencies, we now have something that's doing this, where this is plus 20 dB per decade. Then what happens? Do I continue at that rate forever? My pole kicks in and cancels that slope, doesn't it? And at high frequencies, what's my gain? In absolute sense, you have S over S, don't you? That's 1. So you have a dB gain of 0 dB. This particular value right here is 0 dB. And where's this magic point? That's breaking at 1 radian per second. What's the phase of this look like? How many phase terms do you need to look at? And now we should be giving hand signals, right? 2. Do I see a 3? We'll take bids here. We'll have an auction. How many terms do I have to consider for creating the phase? We have the sine to worry about, don't we? That sine is minus 180 degrees for all frequencies. We need to make sure and keep track of that. So now we have, if we looked at this phase Bode plot, and what frequencies do we need to worry about? Well, the 0 is always on, so let's just worry about it relative to sort of what's happening at 1. We'll go a decade below that and a decade beyond that, and that really gives us enough frequency expanse. But we do have minus 180 degrees due to the constant of -1. That's our sine. We have a constant of -1, and we could write that as 1 at minus 180 degrees. It didn't impact our magnitude response, but it does influence our phase. And you could argue, well, why don't you put it at plus 180? That's fine, but I usually just make it negative because typically we think of things being delayed from the input. So if we give it a minus sign, that's more consistent with the delay. But you could have said, well, 1 at minus 180 is equivalent to 1 at plus 180, and that's correct. That is true. But let's just agree that we'll keep it at minus 180. What's the phase of the 0 at the origin? That's plus 90, isn't it? We've already accounted for that negative sign, so now we look at the 0 at the origin. And that's for all frequencies. This is due to the 0. Then we have the phase due to that pole at minus 1. And our phase transition is spread over 2 decades, centered about the break frequency, which is 1. So we go down a decade before, we go up a decade beyond the break, and we know now that we will be living between minus 90 degrees, since it's a pole, and 0 degrees, and we'll just connect that up right there. And this is our phase due to the pole at s equal minus 1. Those are our 3 component parts. We now need to put those 3 pieces together, and all we're doing is starting at the left and adding together as we look at each one's contribution on sort of each frequency, which is a vertical line. Where are we going to start our phase? That phase will begin at a value of 90 minus 180 at low frequencies. So we are now looking at starting at minus 90 degrees. And we're happy to just stay there, except now we hit a pole that starts the slope. And now we will be sloping at minus 45 degrees per decade until we reach minus 180. And does that make sense? So here is our phase plot, the red curve. If you go back here and you said, oh, I have a 0 and a pole, the 0 gives me plus 90, the pole gives me minus 90, so I would be at 0 other than that minus sign, and that minus sign gives me minus 180, so I should at high frequencies be at minus 180. This is now the magnitude and phase of that system with R's and C's equal to 1. And that system was an active filter. And what kind of a behavior is this? What type of filter is that? That one's high pass, isn't it? And what's the break frequency? 1 radian per second. And our life doesn't revolve around 1 radian per second, does it? Everything is not designed to be 1 radian per second. That might be a little bit boring. So we might want to change that. Let's now look at how we can change or modify the passband or the frequency behavior of these circuits that we know how to design or analyze. How can we obtain the passband? That's the band of frequencies that we are favoring or wanting to pass. So how can we obtain the passband we want? while still using component values that we have available or that are in the stockroom, while still using component values that we have available. For example, maybe I want to use 10 microfarad capacitors for whatever reason. For example, I want to use 10 microfarad capacitors, and the silly circuit that I just designed had a capacitor of 1 farad, didn't it? And it had a pass band of 1 for that high pass. Well, this is now what is leading us to learn how to scale. We want to be able to frequency scale. That's going to allow us to change the pass band value. And in combination with a magnitude scaling, that will allow us to adjust for keeping or using these 10 microfarad capacitors. Let's now derive some relationships that will allow us to do this scaling, both frequency scaling and magnitude scaling. First, let's talk about them individually, and then we'll combine them. First, let's scale the impedance value. Or that's maybe too vague. Let me change that to magnitude. Scale the impedance magnitude to be consistent with what I just said. Frequency and magnitude scaling. And the notation that I will use is I'm going to have two different subscripts. Subscript 1 will be the original or the initial value on the capacitor or inductor or resistor. Subscript 2 will be the new value or the final value. So in my particular example, my final value, I would want to end up with a 10 microfarad capacitor. That would be the C sub 2. And maybe my original would be C sub 1 as 1 farad. And that would now give me my impedance scaling value relationship. Let's now derive those. What we want the final impedance to equal or to be scaling by K sub m of the original, Z sub 1, where we want this magnitude scaling to be positive. If that's the case, let's look at our different components. Suppose I have a resistor. It has an impedance, Z sub R of R. And now I can say, oh, if I want Z sub 2 to be K sub m Z sub 1, what does that mean in terms of how are R2 and R1 related? That one's pretty easy, isn't it? So if I want to magnitude scale my resistors, if I know my magnitude scaling parameter, K sub m, and if I know my initial resistor values, I now can calculate R sub 2. So if R sub 1 was 1 and my K sub m was 100, then R sub 2 is going to be 100. That's all I'm saying. I'm magnitude scaling that impedance of my resistor or resistors. What about the inductor? The impedance of an inductor is J omega L in the frequency response relationship, not the S. We need to be looking at frequency response or J omega. So now I want Z sub 2 to equal k sub m z sub 1. Well, if ZL is j omega L, z sub 2 is j omega L sub 2, and that better be equal to k sub m times j omega L sub 1. And this one also is pretty straightforward. The j's I can cancel. The omegas are the same on both sides, and now I'm just left with L sub 2 equaling k sub m L sub 1. And if I need to magnitude scale my inductors, I just hit the initial value with k sub m. For my capacitor, the impedance is 1 over j omega c. And if I want z sub 2 to equal k sub m z sub 1, now for z sub 2, I have this 1 over j omega c sub 2, and I want that to equal k sub m over j omega c sub 1. Or, if I wanted to look at that a little differently, I could rewrite that. I could put that k sub m in the denominator of the denominator, and in particular, if I put it right underneath C1, now I can see my relationship between the two capacitor values directly. I can now see that C sub 2 is equal to C1 over K sub n. So if I now magnitude scale my capacitor values, I'm dividing by that magnitude scaling K sub n. That's how I can magnitude scale. What about frequency scaling? This one's a little more interesting. But with frequency scaling, I'm wanting the impedances at both frequencies to be the same. So the impedance at the final frequency I don't want that to change, or I want the impedance at the final frequency equals, or impedance at the final frequency equals the impedance at the initial frequency. Or really, I'm looking for z sub 2 equal to z sub 1, using my notation from before. And now in this particular process, let's just suppose that the new frequency is going to be scaled by k sub f of the old frequency omega sub 1, or the initial frequency. That's my relationship for my frequencies. If I look at my resistor, how does the frequency scaling impact my resistor? It doesn't, does it? There's no omega in that impedance expression for my resistor. This final resistor is equal to the original resistor when I'm just scaling the frequency. I don't have to worry about changing the resistors. What about the the inductor? For the inductor, I now have z sub 2 is equal to j omega sub 2 L sub 2. That's just definition of z sub 2. But now I can replace omega sub 2 with this relationship with it, the scaling factor in omega sub 1, to have j k sub f omega 1 L2. But I want that to equal z sub 1, and z sub 1 is just j omega 1 L1. And now if I equate these two, the j's can cancel, the omega sub 1's can cancel, and now I can see that for frequency scaling, L sub 2 is going to be L1 divided by K sub F. So my final inductor's value will be the initial value divided by the frequency scaling. And if my frequency scaling was 200, then my final inductor is 200 times smaller than my initial one. Capacitors. The impedance for a capacitor, Z sub 2, is 1 over J omega sub 2 C sub 2. But that's just 1 over J K sub F omega 1 C sub 2. But I need that to equal Z sub 1. And Z sub 1 is 1 over J omega 1 C1. Again, I can cancel a lot of the J's, the omega 1, and I end up with C sub 2 is equal to C1 over K sub F. And again, my frequency scaling for the capacitors is dividing my initial by K sub F. And now I have all of these different scalings. I can magnitude scale and I can frequency scale, and I can actually put those two together. These two scalings can actually be combined into one process with two different parameters, a K sub F and a K sub M, floating around. The two scalings can be combined. If I combine for my resistors, the frequency didn't have any influence, but the magnitude was K sub M times R sub 1. My inductor, the final inductor, the magnitude scaling was upstairs, the frequency scaling was downstairs, and now if I need to do both, that's the combination that I use to scale my inductors. And finally, my capacitor, I have a C1 over K sub M, K sub F. And those are now my scaling relationships for magnitude scaling and frequency scaling. Magnitude scaling because I may want to use a particular parameter value, frequency scaling to give me the frequencies in my filter that I want. Let's use this to build up a particular filter. Suppose I want to, and now we're going to your favorite, word problems, right? So now I can give you some more word problems. Design a first order low-pass filter with a bandwidth of 100 hertz, a gain of 2, and use a 1 microfarad capacitor. So we need a low-pass filter, first order. We want the gain in the pass band to be 2, and we want the bandwidth to be 100 hertz. If you just barely get into chapter 15 and find the first figure, that would be an active low-pass filter circuit. This circuit now, if it's active, it's this op-amp. We're going to connect the non-inverting terminal to ground, and then we're going to have some parameters around that particular op-amp. And in particular, what we want is we're going to have, going into this, a resistor. Let me call this R1. That's now my, let's say, my input resistor. And in the feedback path, I actually have a combination. I have a resistor in parallel with a capacitor. And if I wanted to think of this in a general sense, if this is now my input impedance, and this combination is my feedback impedance, Z sub F. And if you just think in terms of Z sub I and Z sub F, hopefully you can actually see what the transfer function is between the input V sub I and the output V sub O. It's just minus Z sub F over Z sub I. If you just put those boxes in the appropriate location and solve for this transfer function, you would get minus Z sub F over Z sub I. Just do the standard inverter circuit with R1 and R2, and you get minus R2 over R1. We've just generalized that to be impedances now. But what is Z sub I? Now we can plug in these specific impedance values. What's the input impedance? That's pretty easy. That's just R1. What about the output impedance? Z sub F. So that's just this parallel combination of R sub 2 and C, isn't it? Sort of abusing notation, so that now I have R2 times the impedance of the capacitor over their sum. But if I put those both over a common denominator, which is SC, upstairs I just have R2, and downstairs I have S R sub 2C plus 1, and that's now my Z sub F. If I put those pieces together, remember R1 was going to be Z sub I, and that's downstairs. I'm going to divide by that, or divide Z sub F by that with the negative sign. I now know that my transfer function between the input terminal V sub I and the output terminal V sub O is minus R sub 2 divided by R1. I'll just go ahead and put that upstairs. S R sub 2C plus 1. That's now my transfer function of that circuit in figure 15.1. And what does that look like? Can you already see what that is as far as a transfer function? How many zeros do you have? Finite zeros. You do not have any finite zeros, do you? There are no finite values of S that cause that transfer function to vanish or to equal 0. So at DC, what's my DC gain? Minus R2 over R1. So in terms of amplification, I have R2 over R1. The negative will just invert the signal between the input and the output. So really my scaling is coming from R2 over R1. All right, well, we can make this even easier if we do our standard assumption on our parameter value. Suppose we say R1 is equal to R sub 2 is equal to C is equal to what? 1. And if I neglect the negative sign for now, because now what do we know about that? That's just going to change the phase curve, and it's just going to lower the phase curve by minus 180. So if you will allow me, I will neglect the minus 1, and I will simply say that Z sub f over Z sub I is now S over S plus 1. Is that okay? H of j omega then becomes 1 over j omega plus 1. I don't know why I changed notation. That's VO over VI, isn't it? But it's also Z sub F over Z sub I. Right, I pointed right there. Can you see my finger? It's now Z sub F over Z sub I. If I neglect the minus, that's what I'm saying. What are you asking? I don't understand. Yes, thank you. So I was going back to the last example. That's now 1 over S plus 1. Thank you. Is that better? Now are we on the same page? So now my H was correct, 1 over j omega plus 1. And what's my cutoff frequency? The value that causes my real part and imaginary parts, it's just one factor, one linear factor in the denominator, and omega equal to 1 will allow my real part and imaginary parts to be equal, and that's my cutoff frequency. And you just told me the DC gain was equal to 1. Right now. And we need to change that, don't we? We need to make that 2, but let's not worry about that yet. Let's first figure out, because the denominator, the pole is going to be influenced by this R sub 2c time constant. If I can pick that, then the R sub 2 might be fixed, but I still have flexibility in R1 to adjust the numerator. So I probably want to go ahead and fix C and R sub 2. C I wanted to fix based on using a 1 microfarad capacitor. The C is fixed. On the exam, you could say, oh, C is equal to 1 microfarad. And I'd give you 1 point out of 25 for that, right? You wouldn't lose points. That's correct, isn't it? So your final capacitor C is 1 microfarad. You could do that without even doing any design, right? You at least got that out of this lecture, I hope. So now we have that, but let's now design for the bandwidth that we wanted. We wanted a bandwidth of 100 hertz. And this right now has a bandwidth of 1 radian per second, different units. We need to frequency scale our parameters in order to give us the correct bandwidth. We need to find what K sub f is. What is our frequency scaling? And we could say, well, that's the new frequency over the old frequency, or that's omega 2 over omega 1. What was omega 1? That was 1, but its units were radians per second, weren't they? So omega sub 2 better be in radians per second, and we needed 100 hertz. So this is now 2 pi times that 100. Or our K sub f is 200 pi, or 628.3. So that's now our frequency scaling, and we would then put that K sub f into all of these formulas right there. That's not going to impact our resistors yet, is it? But now we need to find the magnitude scaling, or now what we will do is use the required capacitor value and what we've just found for K sub f to find the magnitude scaling to find K sub m. If we use the combination of magnitude and frequency scaling, we now know that C sub 2, which is our new capacitor, and you know what that needs to be. That needs to be 1 microfarad, needs to equal C1, which is our old capacitor, divided by K sub f, K sub m. We know C sub 2. We know C sub 1. That was 1. We just found K sub f. The only unknown in that equation is the K sub m, and we can solve for it. K sub m is now going to equal C1 over K sub f C sub 2. Or that's 1. That was 1 farad for C sub 1. K sub f was our 628.3. That was our frequency scaling. And C sub 2 that we said we wanted to use was 1 microfarad. And now we know that K sub m is that particular product, which is going to be 1,591.6. Now it gets confusing because I had R1s and R2 in my circuit, didn't I? So I'm going to use a different notation. I'm going to call them old and new. Is that going to be okay? I need to find a new R sub 1 from the old R sub 1. I need to find a new R sub 2 based on the old R sub 2, meaning right now, this was my original circuit. R1, R2, and C were all set equal to 1 initially. But I want CC to be 1 microfarad, and I want the bandpass interval to be 100 hertz. So that now needs to be 2 pi times 100, and that now gives me a C equal to 1 microfarad. Now I need to adjust R1 and R2 to give me my passband that I want. Meaning R sub 1 new is equal to K sub m R sub 1 old. K sub m was 1,591.6. R old was 1. So my new resistor value is 1,591.6. R sub 2 is exactly the same thing, wasn't it? Because it started out being 1, so it's now 1,591.6 ohms also. Pardon? So now what do we need? Now we need, if we go back to our original word problem, what have we accomplished? We're using our 1 microfarad capacitor. That's good. We've accomplished our bandwidth of 100 hertz, but we haven't yet touched the gain of 2, have we? We didn't do anything yet with adjusting the gain. So if we go back to our original transfer function, right there, we can adjust the gain by adjusting R sub 2 or R sub 1. Which would you pick to adjust? If you pick R sub 2, that messes up your frequency, doesn't it? Or your time constant. So let's leave R sub 2 alone and adjust the gain by the choice of R sub 1. Is that clear? If we started messing with R sub 2, that has impact in 2 different places, the gain and the frequency. If we adjust R1, we leave the denominator alone, which is already establishing our bandwidth, and we can simply adjust the gain in the passband. And we want that gain to be 2. Meaning, we initially, or right now, without going any further, presently, we have a gain of 1. We can adjust R1 or R sub 2 let's say to change the gain. But what we just observed, hopefully, by looking at the transfer function, however, R sub 2 also influences the bandwidth or the cutoff frequency. For that reason, let's now use R1 to adjust the gain. And we need R2 over R1 to equal 2. So R1 needs to be half of R sub 2. So that now R sub 1 is R sub 2 over 2, which is now this 1591.6 cut in half, or 795.8 ohms. Questions on that example? Yes. So the question was, if we're doing this design on the exam, do we have to stick to K sub F and K sub M for frequency scaling and magnitude scaling? My initial answer is yes. It'll be easier for me to grade if you stick with that, and I'll know what you're doing. If you do something else, I may not be able to give you as much partial credit. But if you have another approach to doing or picking your parameter values to design the filter, you can write me a note and say, I'm doing it based on this approach or this technique. And let me know what you're doing. Other questions on this? Yes. So now the question was, if you now have it looks like it would be okay with the band or the low pass and the high pass because you really just have this one frequency to worry about. Now with respect to a band pass, you have to worry not only about sort of the center of that band pass, but also its width. And that's the Q that was referred to earlier. You need to worry about the Q. Oh, I guess she's telling me that we're... So yes, it's a little bit more interesting, but you can still scale all of these parameters with the same scaling factors. You can do a magnitude scaling and a frequency scaling. It's just that the band pass or the region will scale to whatever it was percentage-wise in the original design. So if you're okay with that ratio of center frequency to band pass region, you're okay with these formulas. We'll pick up somewhere close to that on Thursday.